On scales far beyond human perception, there are strange beasts. Exquisite palaces, wondrous landscapes. Some just a few thousandths of a millimeter long. Others dominate the vast expanses of the cosmos. Thanks to groundbreaking new technologies, I'm setting out to explore these hidden worlds for the first time.
You're looking at the craters and bumps and hills on the skin of bacteria.
Mind-blowing to look at that.
Each one of these dots is a galaxy. We have an instrument here that allows you to look at an atom.
We can block the COVID-19 virus itself.
And at the tiniest and the largest scales, I'll see how physics has bizarre consequences.
My journey will take me to the frontiers of modern science, revealing our latest discoveries and our biggest unanswered questions.
This is the story of how the universe works at scales we can't normally see, from nanoparticles to galactic superclusters. These are the very first images ever recorded of the microscopic world. They appeared in a book called Micrographia, written by the 17th century scientist Robert Hooke using the first microscopes. Even at this magnification, they seem so unfamiliar.
With Micrographia, 3.5 centuries ago, Hooke started us off on a voyage of discovery into the universe at ever smaller scales.
As we began to see the microscopic world, we realized that it's very different from our own. These tiny insects have evolved extraordinary adaptations to navigate the world at scales we can barely imagine. Because when you're this small, the laws of physics have unexpected consequences. This is a type of wasp called Megaphragma, one of the smallest flying insects in the world. It's just a few tenths of a millimeter long, some 5 or 10 times smaller than a flea. It has wings like paddles and flies in an unusual way.
That's because air feels very different to it than it does to us. We're barely aware of the air around us as we move through it.
And that's because of the science of air resistance. Take a golf ball and a ping pong ball. It's easier to throw a golf ball than a ping pong ball. They both have the same surface area and so feel the same air resistance. But the ping pong ball is lighter, with less momentum, and struggles to push through the air. Megaphragma is like a tiny ping pong ball, with little momentum for its surface area. So to it, the air feels more like a liquid, and it's evolved its unusually shaped wings to swim through it.
If you were to make this the size of a human, then it'd be barely able to move its wings, let alone use them to fly. Yet it's so successfully adapted to the world in which it exists that in recent years, entomologists have found them all over the world, from Africa to the Pacific to South America, even in the woods outside London.
When we look at even tinier objects, 10 times smaller than Megaphragma, we come to the scale of a typical animal cell. As we increase magnification, the laws of physics become ever more strange. Professor Susan Anderson at the University of Nottingham uses powerful optical microscopes to study human heart cells.
So what is it we're seeing there?
So this is the sort of detail that we get in a light microscope. We have lots of individual cells here, so we can see individual cells. In each you can see nuclei, so these are the nuclei. The little bright spots are the nucleoli. This is the edge of the cell, and then the cytoplasm of the cell, you can't really see any detail inside.
So why is it that you're looking at these?
The useful thing about this is that we can see cells, dynamic cells. So the cells that we're looking at here are human heart muscle cells. So we can actually see them beating.
Oh, wow. Right, yes.
Yeah.
Seeing them beat in such detail means scientists can begin to understand why they go wrong.
You can see the nucleus, you can see the outline of the cell here. You can see lots of them beating at about 30 beats per minute, which is about half the rate of a human heart.
They're from a living heart?
It would be difficult to do that ethically. So what we do is we obtain stem cells from human skin. We reprogram the human skin cells back to stem cells, and then we direct them down a differentiation pathway to being muscle cells. And we can obviously see that they are contracting and beating like a heart muscle cell.
What's actually happening here?
The cytoplasm contains lots of contractile filaments, and they're shortening and lengthening so that the cell beats. There's a whole community of cells here that are talking to each other, and they're passing that signal from cell to cell, and they're beating en masse.
How does it make you feel when you're looking at these living cells?
I love them. They've got personality. You know, they do what they want. If the light here is too bright, they will just move. They will just walk away. They're very entertaining.
Microscopes are key to understanding cells because right across the living world, they're tiny compared to most everyday objects. For instance, a 200-ton blue whale and a tiny megaphragma are both made of cells that are similar in size, roughly between 100th and 1/10 of a millimeter across. Why are cells this size?
The answer lies in the fact that in certain crucial ways, small things are much more effective at interacting with the outside world than big things. Here is a lump of titanium. It's a very reactive metal, and I'm going to try and burn it. Nothing. But here is also titanium, but it's been crushed down into a powder.
Powdered titanium has far more of its surface relative to its volume exposed to the air. So it's got much more access to the oxygen in the air to help it burn. This applies to cells too. Cells absorb nutrients and oxygen from the outside.
Being small and therefore having a large surface area to volume ratio means they can do this very effectively. If they were significantly larger, they wouldn't be able to take in what they need to survive.
Ultimately though, there's a limit to how small they can be. Cells are full of stuff, the nucleus, mitochondria, ribosomes, so it's a balance between making them small enough to maximize their surface area to volume ratio, yet big enough for their parts to perform their function. And their shape is crucial too. For instance, some cells have found a way to increase surface area without changing volume. The cells in the walls of our digestive tract absorb the nutrients needed to sustain our entire body through their surface. So this surface needs to be as large as possible.
How do they do this? How can cells maximize their surface to volume ratio without getting any smaller? Well, imagine this balloon as one of those cells. How can I increase its surface area without making it significantly smaller? Well, I can give it fingers. I've calculated these 5 fingers increase the surface area of this rubber glove by about 50%. And remarkably, Evolution has adopted precisely this strategy. Welcome to my digestive tract. These protuberances are called microvilli. They're each about 1,000th of a millimeter long, but just a few molecules wide. And there are millions of them. They stick out from the cells, dramatically increasing their surface area and therefore their ability to absorb nutrients.
Of course, the real thing is rather more impressive. Scientists have calculated that because of the microvilli, our intestines have increased their surface area by up to 15 times. Modern optical microscopes have uncovered a strange world, just a few thousandths of a millimeter in scale, a world very different from our own. All revealed by a device that is essentially remarkably simple.
This is a modern but pretty basic compound microscope, and it works on the same principles as Robert Hooke's microscope from 400 years ago. It's so simple really because you just have two lenses, one in front of the other, and adjust them until you get the sharp magnified image.
The second lens multiplies the magnification of the first. There is, however, a fundamental problem with optical microscopes. As we increase magnification, images get more and more blurry. This is because light is a wave, so objects which are smaller than its wavelength are impossible to see clearly, which means optical microscopes hit a wall at about 1,000th of a millimeter. So the next step downwards means ditching light entirely and finding something else to see with, like tiny subatomic particles, electrons. I found a bit of old technology, something older viewers might recognize.
I've taken the back off this old TV set. So what you can see here is called a cathode ray tube.
This bit, the cathode, boils off electrons, which are then accelerated in a vacuum
to hit the phosphorus screen at the front. Now, ordinarily on a TV set, the electron beam scans across the whole surface of the screen to produce the picture. But I've rigged this now so that it produces just a single narrow beam of electrons forming a spot in the middle. Now, because electrons are negatively charged, they're affected by a magnetic field. In fact, that's how we control the direction of the beam. And to show that, I've got a small magnet at the end of this stick, which I can use to distort and move the direction of the beam. In fact, you can see it's produced 3 spots. That's because there are 3 electron beams, because this is a color TV. Now I've got it working normally. The electron beam is scanning across the whole screen to produce the full picture. But I can still distort this picture using my magnet. So if magnets can be used to control and direct the path of an electron beam, they can also be used to focus a beam of electrons in the same way that a glass lens can be used to focus a beam of light. And this means that we can use electrons to make an electron microscope. This is a modern electron microscope, and in many ways it resembles Robert Hooke's optical microscope from 400 years ago. But this one uses a beam of electrons, just like in the back of that old TV set.
Here's where the electron beam is generated. Electromagnetic lenses focus the beam here. This is where the object is placed. More lenses here magnify the image thousands of times, and this is a screen which turns the electron image into something we can see.
With microscopes like this, scientists were suddenly able to see objects hundreds, even thousands of times smaller than they'd ever been able to before.
We could see tiny details on the bodies of insects and the machinery within cells that made them function. And then we came face to face with one of our deadliest enemies. This is an infectious bronchitis virus, and these are common cold viruses. On them, you can see something strange, a kind of halo surrounding the virus.
There were, in fact, tiny spikes, each one just 100 millionth of a meter across. And they gave the virus a crown shape. So they named this new class of viruses after the corona of the sun. These are all coronaviruses.
In 2020, electron microscopes helped to identify a new virus.
SARS-CoV-2, or COVID-19.
Professor Pippa Hawes studies viruses like COVID-19 for the Pirbright Institute.
How have electron microscopes allowed us to understand COVID-19?
They've been crucial because they've allowed us to investigate the structure of the virus so we can actually identify it. So here we have the COVID-19 virus itself. We can see the spike protein very, very clearly here around the outside of the virus. And inside is the viral RNA.
Like all viruses, COVID needs to hijack another cell to reproduce.
What does the virus do inside the cell?
It takes over the cell machinery. The RNA gets placed inside the cytoplasm of the cell. This RNA is read by the cellular machinery, and it's translated into viral proteins that the virus is using in order to replicate.
So by giving it its RNA, the virus is basically reprogramming the cell to get it to do its bidding.
Yes, exactly.
Incredibly, we can now see exactly how this happens.
So what are we looking at here? Where's the cell and where's the virus?
The outside of the cell is sort of outside of our field of
okay,
view.
right.
Yeah, so this is zooming in now on an infected cell. These are parts of the cell that the virus has taken over and formed into these double membrane vesicles.
So these vesicles then are like the virus's nest that it builds to make a home for itself so that it can replicate.
Yes, exactly. It's sometimes called a factory. It's where it produces more copies of the viral proteins, it produces more of the RNA, and where it all comes together in the new viruses.
And can we see the individual viruses?
Yes, if we go... Ooh. Here, these two are viruses that are actually budding into this vesicle. So these are forming viruses.
Sneaky.
Yes.
And so understanding this, I mean, does it allow us then to combat COVID-19?
We need to know how the virus infects, how it replicates and how it leaves, which would help with antiviral treatments to prevent the disease.
Seeing things at this scale has revealed an incredible new world to scientists. They could see and begin to understand how genetics worked by seeing single chromosomes. They could watch a white blood cell attacking an infection. And they could now see beyond the living world, deep into the materials that surround us. How cracks move through metals. Then, in 1991, a group in Japan saw this. Strange shapes forming at the end of a sparking filament. 10 times smaller than a virus, they were carbon nanotubes, each a long cylinder whose walls were just a single carbon atom thick. And they had unexpected properties, which has led to an explosion of fascinating new materials.
This is one of the blackest materials in the world. See, it might look to you like a flat black square, but in fact, if you look at it side on, or even at the back, you can see it's got contours, it's got dents. And yet, looking at it face on, there's nothing, just pure blackness. Now, normally when we see objects, light bounces off of them into our eyes at different wavelengths and different angles, so we can see color and shape. But this is like a Harry Potter spell. Light falls on the surface and then just disappears forever.
What's perhaps most surprising is that this paint is made of nanotubes. The paint, called Vanta Black, is the invention of nanotechnology scientist Ben Jensen.
So it just looks like a black surface here, but talk me through what it looks like if you zoom in.
So if you imagine a forest of trees, but the trees are thousands of meters tall, and they're all straight and they're all equally spaced. So light comes in, photons come in, and they effectively bounce between the trees, and then they're absorbed after a number of bounces. So as you can see on here, it looks like a very, very thick, lush carpet. So light coming in gets in between the nanotubes and bounces around and is eventually absorbed into the substrate.
It looks like a brush.
Yes, exactly.
I want to get across to you just how black this material is. This card has been painted with the blackest commercially available paint. It's called Black 3.0. And yeah, it looks very black. But put it alongside the Vanta Black, and if I shine a light on them, you can see the paint just looks grey in comparison. And even more impressive, if I make an angle so that the light bounces off the surface and hopefully into the camera, you can see that this paint looks a lot brighter because the light has been reflected. But if I do the same thing with the Vanta Black, you should see no difference at all. All the light is being absorbed, none of it is reflected. What is it useful for?
So its main uses are in satellite systems for controlling stray light from the sun, the moon, and the Earth when you're looking out at stars. It's also used for calibrating infrared cameras that look at the Earth for global warming studies. And terrestrially, it's used to protect cars with autonomous driving modes from sunlight entering the camera systems and causing ghosting and loss of signal.
For me, this is an entirely unexpected and surprising property of nanotubes. And more importantly, this is nanotechnology that we can see, or rather not see.
Glimpsing tiny nanotubes was impressive, but could we go even further? By the 1980s, scientists were trying to see ever smaller things using a completely different approach.
They wondered if they could see by feeling. Basically, the idea was to mimic the way the needle on an old record player works.
A stylus passes along a groove on a record, and the tiny bumps vibrate the needle, making music.
But of course, the tip of a record player stylus is far too big to feel something as small as an atom.
But then in 1982, two scientists, Heinrich Rohrer and Gerd Binnig, had an ingenious idea. They put a thin metal spike into a corrosive liquid.
Using electrical currents, they slowly dissolved away the tip of the spike so that just a very thin needle of metal remained. Its tip was just a few atoms in diameter.
But how could this needle see? One idea was to harness an unusual force of nature.
This is a gecko. Its feet stick to the glass using a tiny attractive force called the van der Waals force.
Van der Waals forces exist because of a rather quirky aspect of atoms and molecules. Think of an atom as a tiny positively charged nucleus surrounded by a cloud of negatively charged electrons.
But crucially, these electron clouds aren't static. They fluctuate in shape, often randomly. So the clouds can become lopsided, with more electrons on one side than on the other.
Because opposite charges attract, the negative end of one molecule is pulled towards the positive end of another.
The force that an individual atom feels is, of course, minuscule.
But these effects can add up.
And this, in turn, means that the molecules on the surface of an object can sometimes feel pulled towards the molecules on the surface of a nearby object.
And that's what the gecko is taking advantage of.
A gecko's feet are covered with billions of tiny structures called spatula.
When these press against the glass, they flatten out, creating a huge surface area. Billions of atoms are now in contact. Then the tiny van der Waals forces combine and hold the gecko in place. And this was one of the forces Binnig and Rohrer believed they could harness.
When a tiny stylus, and remember its tip is just a few atoms wide, approaches atoms on the surface of the material, this is when the van der Waals forces come into play. Just like the spatula on the foot of a gecko feels an attractive force between it and the molecules on the surface of the glass, so the stylus feels a force pulling it towards or pushing it away from the atoms as it passes over the surface.
Measuring minuscule forces like these can paint a picture of the surface at the tiniest scale. This is a modern atomic force microscope. Dr. Georgina Ben is using it to understand one of our deadliest enemies.
I'm going to be imaging E. coli, which are a type of bacteria. So with a normal microscope, we could look at just the bacteria, but we need our atomic force microscope to be able to see the details on the surface.
Why are we looking at the surface of E. coli?
So E. coli are really good at resisting antibiotics because they have this extra protective layer around the outside. And we want to know how the protective layer is arranged so that we can help people design antibiotics that can get through the protective layer more efficiently.
So this is the full cell, the full bacteria.
Yeah. So you can sort of start to see features on the surface. And these are already well below optical microscopy kind of sizes. Right. My scan's going to be 500 nanometers wide.
So we're now looking at the surface of the bacteria.
Yes.
This is really impressive. What we're looking at here is bacteria skin, and it's, you're looking at the craters and bumps and hills on the skin of bacteria to find these weak spots that we can attack with antibiotics.
Each one of these black spots is a hole on the bacteria, which is about 3 millionths of a millimeter wide.
These are the holes that let water and nutrients in and out of the cell. So we're looking at how they're arranged relative to each other. And what's interesting is that you've got this really tight lattice of pores, and then sometimes there are these gaps in your lattice.
So those are the weak spots?
We don't know. So we want to know, that's like a next question, is why these are important, why they would be there in the first place. So we know that some kind of patches will make the membrane weaker, and some of them will not.
So if you could get the bacteria to mutate so that it generates these weak spots,
or
then
maybe,
you can attack it.
Yes, or maybe get a drug that will make these weak spots, and then we could apply antibiotics.
With the atomic force microscope, we began to see more detail of the world than ever before, but it had its limitations. They are most effective at seeing features on a flat surface.
But atoms also connect up in 3 dimensions, often forming very complicated shapes, which in turn affects their behavior. How then can we see these shapes? Remember how visible light has a limit because of its wavelength? Well, it turns out there's another form of light which has a much, much smaller wavelength.
X-rays.
Crucially, X-rays have very short wavelengths when compared to visible light. Now, the wavelengths of visible lights are just under 1/1000th of a meter, but the wavelengths of X-rays are typically several thousand times shorter, at around 1/10th of a billionth of a meter. But there are many differences. Our eyes can't detect X-rays. More importantly, they pack a punch. X-rays contain much more energy than rays of visible light. The intense energy of X-rays enables them to pass unhindered through soft tissue like flesh and blood, which is as transparent to X-rays as glass is to visible light.
The larger atoms that make up our bones do stop X-rays. So when you see an image like this, you're literally seeing an X-ray shadow cast by your bones on photographic paper.
This begs the question, can X-rays, which have such short wavelengths, be used to see things that are just too small for visible light?
The first hints that this might be possible came in the early 20th century. Scientists noticed that when they shone X-rays through crystals, they produced weird spots arranged in patterns.
These images may not look like much, but think of them as a kind of code. And by cracking it, you can deduce the way the atoms in the crystal are arranged. This process of turning images like these into an understanding of how substances are structured down at the atomic scale is known as X-ray crystallography. For a sense of how X-ray crystallography works, let's say each of these Christmas trees represents one of the atoms that makes up the crystal.
To keep it simple, let's say they're all arranged in neat rows, just like these trees.
What's important is that the wavelength of the X-rays striking the crystal is about the same as the distance between the rows of atoms, or the rows of trees in our analogy.
Imagine an X-ray reflecting off the surface and the layer beneath. The beam that travels down to the next layer has a longer journey, and that is key. If the waves are now out of step and the peak of one coincides with the trough of the other, they then combine and cancel out. But if they're in step, the peaks combine, making a larger wave and a bright dot on the screen.
By carefully measuring the angle at which the X-rays strike the crystal, where the dots appear, where they disappear, you can deduce the structure of the crystal. By decoding images like this, scientists in the early 20th century were able to deduce the structures of simple crystals like rock salt. The atoms are arranged at each corner of a cube, and the cubes repeat to form a 3D lattice. Most importantly, it meant we now knew the distance between the atoms. It's 1/3 of a billionth of a meter.
But for me, the story of X-ray crystallography really comes into its own because of one of the great heroes of British science, Dorothy Crowfoot Hodgkin. At Cambridge and Oxford in the 1930s and 40s, Hodgkin became fascinated by X-ray crystallography, and she quickly established herself as one of the leading researchers. Her first big challenge came during the Second World War and her work on penicillin.
Scientists had already noticed that the newly discovered penicillin had incredible antibacterial properties. It could stop infections in their tracks, literally bringing patients back from the brink of death. Now, in the throes of war, understanding it and producing it in quantity was more important than ever.
But penicillin was still a mystery, with a handful of atoms arranged in an unknown structure. So Hodgkin set her laboratory a challenge: use X-ray crystallography to learn its structure. Georgina Ferry is a science writer and biographer of Dorothy Hodgkin.
Tell me about penicillin. What was so difficult about understanding its structure?
The structure was unknown. And naturally, the organic chemists all came to Dorothy and said, would you like to have a go at this? The first problem with it was that it doesn't make terribly good crystals. These are not ideal for putting into the X-ray apparatus. It took a while before they managed to get a version of penicillin that she was able to get a good image from. That image looks like this. So these are spots on photographic film that have been made by X-rays coming out of the crystal and hitting the photographic film. The dots are at different intensities. Some of them are very black. There's some down here that are very faint. And what she had to do was carry out a complicated mathematical calculation, which then enabled her to begin to understand where there was what's known as density in the molecule and in the crystal. And density means there's an atom there. And the final stage, once you've done all those calculations, is to essentially draw a contour map. This represents a slice through the molecule, and the numbers that are written down represent the density of the electrons. And what she's done is join up areas of equivalent density, and that shows you that's a place where there's an atom because there's a lot of intensity there.
We're looking at a 2D picture here. So how did Hodgkin then go to the full 3D structure?
What you want to do is take a number of slices, stack those one above the other, and that'll show you the three-dimensional structure of the molecule. So you can see what we've got here is a stack of perspex sheets at equal distances apart, and on each sheet you've got the contour lines drawn, as we were looking at before. And if you're looking down from the top, you can see the three-dimensional structure.
This is the structure of penicillin that Hodgkin came up with after some 4 years of research.
These are the carbon atoms, and they're connected by chemical bonds to other atoms.
Oxygen, hydrogen, nitrogen, sulfur.
But it's this section here that explains its incredible efficacy. It's called a beta-lactam ring, and it seems to give penicillin its wondrous ability.
It binds to a part of the cell wall of most bacteria, killing them dead. Understanding how penicillin works was a revolution in medicine. Hodgkin's work spawned a generation of new antibiotics, effective against many aggressive bacteria, saving millions of lives. And these techniques, still widely used today, famously went on to unlock the structure of DNA. Despite the achievements of X-ray crystallography, it was still an indirect method of seeing and only worked for crystals. To see even smaller things would require something else. It seemed electron microscopes held the most potential, but they had a huge technical problem. Their electromagnetic lenses were fundamentally different from glass ones.
One of the most common problems that affects lenses is called spherical aberration. You see, the way lenses work is that they bend the light that travels through them, but the amount of bending depends on which part of the lens the light travels through.
So when I try to focus the sun, for instance, I can never quite focus to a point, which means at high magnifications especially, parts of the image will always blur.
Electron microscope lenses are exactly the same. They also suffer from spherical aberration.
And at high magnification, the blurring was making the images unusable.
Now, for glass lenses, this issue can be minimized. You add a second lens, a concave lens, which corrects for the first one, giving us a much sharper point.
But this solution doesn't work with electron microscopes.
The lenses of electron microscopes are fundamentally different from glass ones. There simply is no equivalent of a concave lens. The physics of electrons and electromagnetic fields forbids it. So it seemed that electron microscopes would always suffer from blurriness at very high levels of magnification. The question was whether we could delve deeper to see even smaller. Well, the next breakthrough that changed everything took place here in Germany.
Two teams of headstrong scientists started to question the orthodoxy. There were three in Germany: theoretician Harald Reuser, experimentalist Max Heider, material scientist Knut Urban, and an American team led by Andrei Krivenik.
Everybody expected us to fail, and so we knew we could only exceed expectations.
Each stubbornly believed that they could somehow overturn the established prevailing science and make an electron microscope that could see more, perhaps even atoms.
Was it a big challenge then to persuade the science world that here was something that was going to change the field?
The science world at that time had essentially given up to have aberration-corrected electron optics.
They decided that hardware aberration correction will be unthinkable.
They said it was impossible.
It was possible. We had three different people: theoretician, experimentalist, and material scientist. And I think these three together, that was just the point for the success.
Their approach used multiple electromagnets, multipoles, to distort the image, squeezing out the worst of the aberration. Then a second lens reformed the image, now almost aberration-free. But getting it right was challenging. It would require sophisticated arrangements of multipoles, sensitive cameras, and powerful computers.
And here, for example, we have one hexapole, and as you can see here, we have 6 poles with 6 coils. They are just connected to each other, and then we have a north, south, and the beam passes through this hole here. That means first we change the shape of the round beam to a triangular shaped beam, and then to combine it with second hexapole to have a round beam again.
For years, they struggled to get their new lenses to work, and the rest of the scientific community remained skeptical.
I had a lovely comment from a professor at Stanford who told me, Andre, you're bearing your career.
But then, in June 1997, their stubbornness began to pay off. And soon they caught glimpses of the building blocks of all matter with unprecedented clarity. Here's a typical image without aberration correction. Now watch as it's added in. The white blurs resolve into 2 clear dots, each one a single atom of silicon.
Finally, you could see atoms.
This was a real jump in innovation. This was a real paradigm change.
What was it like when you saw those first images?
Seeing is believing, and the mission impossible was not impossible.
They had achieved a scientific miracle.
It was like if you have a huge fog, but suddenly the fog goes, suddenly you see everything.
A new kind of electron microscope.
It was brilliant, everything was so unbelievable. And this is the most important effect of aberration correction.
By 2020, they'd gone from academic outcasts to world-renowned scientists.
The images that came out are truly spectacular. Like one of them on the cover of Nature, that's kind of like if you're a model and you get on the cover of Vogue.
And they had defined a new kind of science.
I think we are on the way to make high-precision electron microscopy a part of science in general.
The next stage of this journey downwards happened in Manchester with the discovery of an incredible new material, graphene. The new electron microscopes revealed that graphene was a sheet of carbon just a single atom thick. And incredible strength was just one of its unexpected properties.
So, just how impressive is graphene? Well, I've come here to this lab to carry out what's called a stress test. I've got two strips of plastic here. It's a stretchy polymer. One of them is just the pure polymer. The other contains just 3% graphene mixed in with it. And I want to stretch them to find out how much force is needed to snap these strips.
First up is the pure polymer.
There we go.
It's gone.
It's gone.
So that snapped at
533 newtons.
533 newtons. So that's about two
bags of cement.
2 bags of cement. So now you're going to swap it with the graphene.
Yes, I'm going to
implanted one.
reset the machine with the graphene ones. Okay.
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 Okay, so it's now hit 500 newtons. We've now already overtaken the non-graphene.
Yes.
And it looks pretty healthy as far as I can tell.
It's healthy, yes.
It's coming up to 750 newtons now.
We're now...
And now it's come up to 1,000 newtons and still going strong.
And...
Oh, so that was about...
So the final force was 1,074.
So that's double. Twice as much force was needed to snap this polymer compared with the one without the graphene. That is pretty impressive. A huge improvement with just a few percent of graphene mixed in with the polymer. That's incredible.
Graphene has shaken the scientific community to its core, and yet was discovered almost by chance by scientist André Geim as he was searching for ever thinner slivers of graphite.
Talk me through what happened on that night when you realized your eureka moment.
20 years ago, I realized that just taking Scotch tape, putting piece of graphite between the Scotch tape, peeling the Scotch tape like that, leaves small pieces of graphite.
Is it something we can demonstrate here? Because we have a piece of graphite.
Yeah. You can take this piece of graphite and without much trouble, you can, of course, make it thinner by repeating this procedure. But if you shine lines through, you eventually start finding flakes which are transparent. And that actually was eureka moment, because being reasonably well educated, I realized that if flakes of graphite transparent, they are really, really thin. Probably initially those were 10 layers thick, but eventually we went down to a single layer.
It's hard to overstate just how excited scientists and engineers are about graphene. So let me just remind you what graphene is. It's just a single flat sheet of carbon atoms all bonded together. But that would be really underselling it, because at around 1/3 of a nanometer, it's just a single carbon atom thick, making it the thinnest material ever made.
For a sense of why graphene is so extraordinary, we have to understand its physics at the atomic scale. Each sheet is made up of repeating hexagons. At each corner is a carbon atom that's bonded powerfully to 3 others. Those bonds are the source of the material's strength, but they also seem to produce other strange properties.
Each carbon atom bonds to its 3 neighbors by sharing electrons with them. But not all the electrons are used for this. 1 electron from each atom is spare. These free electrons can zip around unhindered. And this has huge consequences because it means that graphene can be made to conduct electricity incredibly efficiently.
There are high hopes that it will enable new kinds of electronic components, revolutionizing batteries with much greater storage, and also solar power generation, water filtration, material science, and quantum computing.
Of course, this is still early days in graphene research, but there is without doubt much to play for.
The discovery of graphene brings us towards the end of this story, because with the newest aberration-corrected electron microscopes, we're now able to see on the smallest scales imaginable. Professor Quentin Ramas runs some of the biggest electron microscopes in the world. He's going to zoom into a sample of graphene until we can see individual atoms.
Okay, what are you going to show me here?
So we've prepared some graphene samples for you.
The samples are on a copper grid, just millimeters wide.
Let me put it here and actually place it into the sample holder.
That's the 3mm sample.
That's the 3mm sample. And now hopefully you can already
see the grid.
So they're essentially just copper bars.
Under the optical microscope, I can just make out holes in the sheet of carbon within the grid where the graphene flakes are. To see them in more detail, he now switches the sample into a powerful electron microscope.
So what we're looking at now is the same image as we had under the optical microscope.
You can already recognize, so those 2 shadows here are the corners of those grid squares. But in the middle here, you recognize what you also saw on the optical microscope, which are those circle holes, inside which is the graphene that we're going to go and look at. Slowly getting closer and closer and closer. We're going to be zooming into graphene much further in.
Almost gives you vertigo when you realize how much we're zooming in. Okay, so what are we looking at here?
This is a patch of graphene that's about 500 nanometers across.
How does this then compare to the thickness of a human hair? It would be
several meters across.
Several meters across in diameter.
Yes.
That's how. Okay.
That's how small it is.
And yet we're still only halfway in our journey down. Not even halfway.
Hundredth of the way there.
Okay.
And so what we're trying to do really is zoom in even further on that little black speck.
Go for it.
So we'll start reducing the magnification slowly. I'll go to magnify it 10 times this time, trying to not go too fast so that you can really keep.
You don't want to spoil the surprise for me, do you?
You don't want to spoil the surprise, no. If you notice the shape of this hole, it's about the shape of Africa, I would say. It's now getting to a size that is more foreign to everyday life, especially when you start realizing that this patch is going to be 100 times smaller still. So let's zoom in and hopefully see what we're here to see, which are single atoms. So this is now that same patch, and you notice that it is very dark. You might just about start being able to recognize some pattern in the middle, some very faint lines which correspond to the hexagonal lattice in graphene. But if you look closely on the original image that we still have on screen here, you see small round blobs that are perhaps a little bit brighter, and they are brighter because those atoms are heavier. And we happen to know they're silicon, but just to demonstrate, I can move that scan box around one of those single atoms, and hopefully it'll light up like a Christmas light in the middle. And there it is. Because it is heavier, it appears brighter on the image.
So that entire bright patch is a single atom of silicon. And yet it's a blob, it's a patch. It's not the picture of an atom that we learn about at school with a nucleus and electrons buzzing around the outside. So what is exactly?
It remains reasonably abstract. What we see is this average structure of subatomic particles, and that gives us this average round shape. We've magnified this sample that we've taken out from our sample box and put into the microscope by several million times to see on the screen this magnification.
So 1/10 of a billionth of a meter. We've come a long way since Robert Hooke.
For me, as a theoretical physicist, an atom is just abstract mathematics, an equation, an idea. But to see one of them with my own eyes, the building blocks of everything, just 10 millionths of a millimeter across, is nothing less than miraculous.
I still can't get my head around the fact that I'm looking at individual atoms. Well, look, I'll tell you. I mean, I've spent my career studying atomic nuclei, but for me, it's been abstract. The notion that we're looking at an individual atom here, and I love the analogy that there are more atoms in a single glass of water than there are glasses of water in all the oceans of the world, right? Atoms are tiny.
They are tiny.
The fact that we have an instrument here that allows you to look at an atom, the novelty doesn't wear off.
It definitely doesn't. No, it might be either simple-minded or single-minded, but it's seeing those single atoms is, I think, something I'll want to do for the rest of my life, and it's just a wonderful thing to see.
We've now entered a realm in which we can see individual atoms, and it's leading us into a new world of single atom physics, chemistry, biology, engineering, and medicine. It's all so new that it's impossible to say where it's going to take us.
But as we learn more about our world, from insects to cells to the atoms that make us, I know there will be many more wonders to discover. Next time, I go big as I journey from our solar system out to galactic superclusters. I'll confront the biggest mysteries in our universe.
And don't miss that next Monday night at 9 here on BBC 4. And get inside science with BBC Sounds. In the latest podcast, a remarkable image of the supermassive black hole at the middle of the Milky Way.
On scales far beyond human perception, there are strange beasts, exquisite palaces, wondrous landscapes. Some just a few thousandths of a millimeter long. Others dominate the vast expanses of the cosmos. Thanks to groundbreaking new technologies, I'm setting out to explore these hidden worlds.
Mind-blowing to look at that.
Each one of these dots is a galaxy. It's sending you a daily email from space.
At the tiniest and the largest scales, I'll see how the laws of physics have bizarre consequences, overturning everything we thought we knew.
My journey will take me to the frontiers of modern science, revealing our latest discoveries and our biggest unanswered questions.
This is the story of how the universe works at scales we can't normally see, from nanoparticles to galactic superclusters. When we move to scales beyond our imagination, the universe behaves in extraordinary ways. But about 3 centuries ago, when objects like this were first created, we had no real understanding at all of the true size of our universe.
You might recognize this. It's called an orrery. And it's a beautiful little mechanical model of the solar system. Now, it's not really a toy. It's been used for centuries to demonstrate the relative orbits of the planets around the sun. But you shouldn't take this model literally, because it's not to scale, both in terms of the relative sizes of the planets and their distances from the sun. Imagine the Earth were about the size of a football. Now, in reality, our planet is 12,700 kilometers in diameter. So this has been shrunk down roughly 60 million times. So what if we were to shrink the sun down by 60 million times so it's the correct size relative to this Earth? How big would it be? We can now see just how wrong the orrery is in terms of scale, because the sun would in fact be this size.
The sun is over 100 times the diameter of the Earth. You could fit 1 million Earth-sized planets inside it. The sun's mass is the source of its immense gravitational power over the whole solar system.
The next question is, on this scale, how far apart should the Earth and Sun be? Again, this is very different from the orrery, because if the Earth is here next to me, the Sun would be 2.5 kilometers away. The distance between the Earth and the Sun is actually a very significant figure in astronomy. You see, in space, distances are so vast that using kilometers soon becomes very impractical. And so astronomers have come up with their own units of measurement. And as it happens, the distance between the Earth and the Sun is one of them.
The Sun is 150 million kilometers from the Earth, a distance known as 1 astronomical unit. So our neighbouring planet Mars orbits the Sun at an average of 1.5 astronomical units. The asteroid belt, containing millions of floating rocks, orbits it between 2 and 3 AU. Jupiter orbits at an average of 5 AU. Saturn at 10 AU. And Uranus at 20 AU. And Neptune orbits at an average distance of 30 AU. Many of us think this is the end of the solar system. But if you travel beyond the planets to about 120 AU from the Sun, you'll encounter a giant, mysterious structure which helps protect us here on Earth. It's a bubble called the heliosphere. The heliosphere was only discovered in the middle of the 20th century, but astronomers of earlier times did glimpse hints of its existence. The clues were in the behaviour of comets, icy bodies of rock and dust which orbit our Sun at different distances.
Comets have 2 tails, which develop as they approach the Sun, and they point in slightly different directions. One of them is made of dust, and it often trails behind the comet in a kind of arc. But the other straight tail, called the ion tail, is made of gas, and that's the one we're interested in. Here's the puzzle that baffled the astronomers of the past. The ion tails of comets always point away from the Sun. It's as though there's a wind being produced by the Sun. But how can this be possible? I mean, space is empty, isn't it? How can there be a wind blowing through empty space?
A clue to this cosmic mystery can be seen when there's a total eclipse of the sun. The sun has its own fiery atmosphere which shoots away from its surface. It's called the corona. It consists of colossal ejections, loops and flares of a kind of superheated gas called plasma. But the plasma extends far beyond the corona, out among the planets.
So the sun does have a wind. It's called the solar wind, and that's what pushes the comet's tails away from them.
The force driving the solar wind comes from the sun's intensely powerful magnetic field.
And I guess a lot of people don't realize that the sun even has a magnetic field.
Yes, it does, that's right, just like the Earth. Now, the sun's is a bit more complicated and it varies, it's a bit more dynamic, but the basic principles are just the same.
At its most basic level, the sun's magnetic field is quite similar to that of this bar magnet.
And you can see quite clearly that there are regions near the equator where the magnetic field lines are basically closed, they're closed loops, whereas over the poles the magnetic field lines actually point out further into space.
At the sun's surface, the magnetic field lines twist and turn, raising the temperature to millions of degrees. This heat makes the charged particles move so fast that they break free of the sun's gravity. The particles then flow out along the magnetic field lines to become the solar wind.
Here they're trapped, here they can get away far from the sun, and that's what forms the solar wind.
Tim has another demonstration to show how the solar winds create the enigmatic heliosphere.
Water coming out of the hose pipe, that's like the solar wind going away from the sun in all directions, and then it forms a boundary all the way around.
The water flowing outwards from the hose pipe collides with the water already in the pan, creating a turbulent boundary.
That's exactly what happens in the solar wind, and that boundary forms actually beyond all of the planets, something like 100 times further away from the sun than the Earth.
The water's forming a barrier here because the water that's already in the pan is stopping it from spreading out any further, provides a natural barrier. What's the equivalent to that when it comes to the solar wind? What's stopping that from spreading out into space?
Right, the equivalent boundary there for the solar wind is actually the tiny amounts of material that live between all of the stars. So we think of space as totally empty, but actually it isn't. There are tiny amounts of dust, gas, and even plasma-charged particles, and collectively we call that the interstellar medium. And that's the material that the solar wind hits that causes this boundary.
The interstellar medium, the stuff which the solar wind is flowing into, is mostly composed of gases, especially hydrogen and helium. Gases can move and flow, so in that sense they act a bit like water.
If we do think of space as a fluid, then the heliosphere is a bit like a boat carrying us through the interstellar medium.
Like the hull of a boat, our heliosphere helps protect us against the interstellar elements and the storms of space.
Space doesn't just contain gas and dust. It's also contaminated with irradiation produced by cataclysmic events like supernovae. Fortunately for us, the magnetic bubble of the heliosphere also acts as a shield, scattering and deflecting much of this radiation and preventing it from reaching us. So, in a sense, our heliosphere is like a life raft, carrying us through the vast and dangerous waters of space.
As it pushes its way through the interstellar medium, the heliosphere even creates a bow wave, just like the bow wave at the front of a boat. It's thought that most, if not all, stars have heliospheres. Our telescopes have taken photographs of other stars whose heliospheres are clearly visible. Sometimes we can even make out the bow wave. In 2020, the European Space Agency launched a mission to the Sun, a probe called Solar Orbiter. And among the scientists who built it was a team from Imperial College London, headed by Tim Horbury.
7:30, and we're due to launch in about 3.5 hours' time. It's really exciting, the tension's really building.
It's looking really good. 1.5 hours to go. Go Solar Orbiter. You see it launch, and then we get this feeling, it's like a vibration of the launch because it's such a powerful event. Just makes you tingle because you know that it's your baby almost, off it goes. I'd already been working on the project for 13 years at that point. Wow. And to have such a personal connection with what was going on was incredible.
For Solar Orbiter's instruments to work at all, the engineers have had to protect them from the extremes of temperature near the Sun.
The heat shield is always pointed at the Sun, so wherever we move around, we orientate the spacecraft so that that is what's pointing at the Sun.
The instrument that Tim and Helen built is a magnetometer. It's mounted on a boom at the back.
The heat shield can get to temperatures of up to 500 degrees when it goes in close, but the electronics, which lives in the main body of the spacecraft, we have to keep that below 50 degrees. So from that front to the back, which is about 0.5 meter, we have to lose all that heat. And it's much better for us actually to be out here, because although it's cold, it's a stable temperature, and that really helps us to keep the measurements stable.
The orbiter takes photographs of the Sun's surface, and the magnetometer measures its magnetic field. The results are then sent straight back to Earth, to the delight of Tim and the team.
Do you want to have a look?
Yes, please.
So this is the kind of data that we get, and every day we can see what the spacecraft is doing and what the instrument is doing.
I mean, it's quite remarkable, isn't it, that it's sending you a daily email from space every day, updating you about the spacecraft.
It really is.
The orbiter has just started taking photos like this, a gigantic eruption of plasma from the Sun's surface. And the magnetic readings will help us understand why all this activity is happening. The aim is for Solar Orbiter to help unlock the mysterious workings of the heliosphere, the bubble which helps protect us on Earth. Every object in the solar system is held in place by the Sun's enormous gravitational power. And as we move beyond the heliosphere to around 100,000 AU from the Sun, it's thought there's one more massive structure out there, a sphere of icy objects called the Oort cloud. At these scales, we start using a new unit of measurement, the distance light can travel in 1 year. So the Oort cloud is believed to extend up to 3 light years in diameter. Now, traveling outwards, I'm going to leave our solar system behind. We now know that the beautiful ribbon of stars we can sometimes see stretching across the night sky is our own Milky Way galaxy. But around 100 years ago, most cosmologists didn't even believe there were such things as galaxies, and the universe seemed a much, much smaller place.
In the first decades of the 20th century, one of the biggest debates in cosmology revolved around a fundamental question: just how big is the universe? Many astronomers believed that everything we could see in the skies, in fact, every object in the universe, was part of one continuous giant structure of stars, dust, and gas, all clumped together. So the argument went, what we refer to today as our Milky Way galaxy was in fact the entirety of the universe. But some astronomers thought differently. They argued that our universe is composed of an unknown number of galaxies, colossal, independent islands of stars located at vast distances from each other. So our Milky Way would just be one galaxy among many. Now, if that idea was right, then the universe would have to be far, far larger than had ever been suspected.
The debate revolved around some mysterious objects in the sky, fuzzy patches of light called nebulae. Although they were very faint, improving technology meant astronomers could start to get to grips with them.
Telescopes of the time were even able to make out structure in some of these cloudy objects, like this large nebula in the constellation of Andromeda, photographed around 1901, 1902. Some astronomers argued that nebulae like this were relatively close to us, large clouds of dust perhaps where new stars were being born. But others argued that nebulae were independent galaxies in their own right, made up of billions of stars at mind-boggling distances away from us.
The debate was solved to a great extent thanks to the astronomer Henrietta Swan Leavitt. For many years, her work was largely ignored, but it's finally being acknowledged by a new generation.
Henrietta Swan Leavitt worked at Harvard Observatory about 125 years ago as a research assistant. We actually refer to them as human computers. But back then, computers were people, mostly women, who crunch the data and do things like measure the positions of stars, their brightnesses, make all these catalogues. She was absolutely dedicated to her work. She catalogued so many stars, looked at so many photographic plates over and over.
So here are some of Leavitt's photographic plates. Tell me what we're seeing here.
Yes, these are photographs of the night sky. They're negative images.
Leavitt dedicated herself to studying a very weird type of star, known as a Cepheid variable. These grow and shrink at regular intervals. So they pulse in brightness at predictable periods, which vary from days to months. Leavitt concentrated on looking for variable stars in two mysterious nebulae, the Small and Large Magellanic Clouds.
I find it hard to believe, looking at a picture like this, she managed to discover and catalogue 1,777 variable stars. Mind-blowing to look at that and think about how kind of painstaking that work must have been. And looking at these stars, she noticed something that I think really just changed our understanding of the universe forever.
Leavitt realized that there was a strict relationship between how intrinsically bright these stars are and how quickly they pulse.
So if we look at these four pairs of lights, the pair at this end are clearly the dimmest, but they also flash the quickest.
Exactly, yeah.
The brightness increases, but the flashing slows down. And at this end, these are the brightest pair, but they're also flashing the slowest.
And that's exactly what Leavitt noticed, that the brighter stars flash more slowly and the dimmer stars flash more quickly. And it's really what her main contribution to astronomy has been.
Here's the reason for its importance. If we see two Cepheid variable stars and they're pulsing at the same rate, then we know they must also have the same brightness. So, if one seems dimmer to us, then we know that it must be further away. Leavitt had found a way we can measure huge distances in space. In 1923, Edwin Hubble pointed a telescope at the mysterious Andromeda Nebula, and he found that it contained a Cepheid variable. He measured its pulse rate to be very slow, 31 days. So, using Leavitt's discovery, he could calculate that it must be very, very bright. But because it looked so faint when seen from Earth, it must be very, very far away. In fact, the Andromeda Galaxy is 2.5 million light-years away. So the mystery of these faint, wispy nebulae was solved. As suspected, some of them are indeed collections of gas and dust relatively close to Earth. But others, like Andromeda, are their own independent galaxies, floating at unimaginable distances from us. So now that we can identify which celestial objects are part of the Milky Way, we can create a map of it, starting with our solar system.
Michelle, I can see the Oort cloud and the sun in the middle.
Yeah, so the Oort cloud is sort of the edge of our solar system almost, and we don't know exactly how large it is, but it's roughly 2 to 3 light-years in diameter.
Okay, let's see what else is in our local neighborhood if we zoom out a bit more. So what is starting to come into shot now?
Yeah, so Alpha Centauri is our nearest neighbor star system, so it's actually 3 stars. 2 large stars and 1 smaller, fainter star as well. Well, we can also see Procyon there. That's about 11 light-years away from us. And then we also have 61 Cygni over here. Compared to our solar system, we're talking about quite large scales now. But to people like me who study, other galaxies and the wider cosmos, this is still a really tiny distance. Like, for me, it's not even a real unit of measure until we get to, 100,000 light-years or so.
So all these stars that we're looking at here, they're just sort of in the way. You want to be able to see way beyond them.
Exactly. Normally, I don't worry about anything that's less than a few 100,000 light-years across.
So let's zoom out much, much further from the stars of our local neighborhood to encounter an important structure in our Milky Way, which is over 10,000 light-years long.
So what we're seeing here now is the Orion Arm, which is our local or our home spiral arm where we live. And spiral arms are kind of the largest visible structures we can see in spiral galaxies. And that's because they're full of the youngest, brightest stars.
The Orion Arm is home to one of the most famous astronomical objects visible from Earth, the Orion Nebula, a dense molecular cloud lit up by the stars it contains. It's well over 1,000 light-years away from us. Moving outwards from the Orion Arm, we start to see the whole structure of our galaxy.
Okay, wow. So there it is, the Milky Way galaxy. Where are we now in the Milky Way?
So if we start with the center of the galaxy here, where we have this bright elliptical bulge, we're about 25,000 light-years away from that, so up here.
And so how far does the entire galaxy stretch?
So we don't know exactly, but we think roughly from end to end, it's about 100,000 light-years across.
It's the force of gravity which creates all this structure. Gravity also draws in hot, young, massive stars to create the bright central bulge. In some regions of our galaxy, the interstellar medium is drawn together into areas of high density, where turbulence sculpts the gas and dust into astonishing shapes. These are stellar nurseries, where pressure from the force of gravity heats up the hydrogen, making it hot enough to ignite fusion. These are the places where new stars are born. But by studying the operation of gravity at a galactic scale, we've encountered a mystery. As our galaxy revolves around the center, what keeps it all together is the mass of all those stars and gas and dust acting as a kind of gravitational glue. During the second half of the 20th century, astronomer Vera Rubin pioneered the study of galactic rotation, she worked with instruments that could measure it with ever greater accuracy. As she did the maths, she realized something extraordinary.
Okay, so we've shrunk the Milky Way galaxy down to manageable proportions, and we're looking at how it's rotating. Now, Vera Rubin was one of the leading figures who realized there was a problem with the way galaxies like this rotate.
Exactly, and so what we've got here is a simulation where we're going to set it up so we've mapped in all of the visible matter we can see, so the stars, the dust, the gas, and the galaxy. And now if we just set it rotating at the speed we know it's rotating at, we can see what happens.
As the galaxy revolves, it drifts apart in all directions, losing its shape.
Okay, so it's not holding together. There's clearly a problem.
Precisely, and this is what Vera Rubin realized. And the problem is, if we just take all the mass that we have here and add it up, there's not enough, it can't provide enough gravity to stop the galaxy from flying apart when it's rotating.
Rubin came to an astonishing conclusion. Either our theories of gravity don't apply universally at large scales, or there's a huge amount of matter there which we can't see. It's now thought that perhaps around 85% of all the matter in the universe is composed of what's known as dark matter. We can't detect it directly, but it must be there to hold our galaxy together. Most cosmologists now think our galaxy is surrounded by a halo of dark matter, a kind of scaffolding which keeps it from flying apart. Some estimates say it could be up to 2 million light-years across. The light we can see with our own eyes reveals just a small fraction of what's really out there. That's because many astronomical objects give off radiation right across what we call the electromagnetic spectrum.
This is the electromagnetic spectrum. On this end, you have gamma rays, which have the shortest wavelength and the highest energy, then X-rays, and then ultraviolet. On this side, you have infrared radiation, and then microwaves, and finally radio waves, which have the longest wavelength and the lowest energy. And this slice in the middle, this is visible light. It's what our eyes have evolved to see. The rest of the spectrum is, to our eyes at least, invisible.
In the past few decades, we've launched telescopes into space that can photograph the universe across the spectrum. And as we look beyond visible light, it's like pulling back a veil, giving us astonishing new insights into the very largest structures, things we never suspected were there. Astronomers take photographs of the same object with instruments sensitive to different wavelengths. They then combine these to produce images that our eyes alone would never see. These incredibly sophisticated imaging techniques have given us privileged glimpses of astonishing events, frozen moments from the birth, life, and death of stars and galaxies. Our ability to penetrate the mysteries of the cosmos has also led to some bizarre surprises. Astronomers have found massive objects in space that effectively give off musical notes.
The obvious question that people would ask is, how can you hear sound in empty space? In space, no one can hear you scream.
Absolutely, but there are still particles in space, very diffuse gas throughout all of space, and it's possible for sound to propagate in that as ripples through the gas.
Using an X-ray telescope called Chandra, Andrew and his team took these photos of a region of space 250 million light-years away. They show massive energy bursts, shock waves rippling out through the interstellar medium. Each ripple is effectively part of a sound with a wavelength of cosmic proportions. Andrew has calculated that these sound waves make one of the lowest notes ever detected in the universe.
You've calculated that the sound is a B flat.
Indeed.
Which is why we're here, because George, who's the senior organ scholar here at St John's Chapel, is going to play us some notes.
First of all, George plays us a B flat in the mid-range of the organ. Every time George goes an octave lower, he has to double the size of the organ pipe he's using. 3 octaves down, and he's using the longest pipe at his disposal, and the note is getting to be as low as we humans can hear.
You can almost hear the individual oscillations.
Indeed,
It's like a pneumatic drill. So we've gone down 3 octaves.
Yes, yes.
But to get to the sound,
we have to go down another 54 octaves. So we're going to have to keep doubling the size 54 times, and it would then be galaxy-sized.
The organ would have to be the size of a galaxy.
Yes.
The note is so low because the object only gives off one sound wave every 10 million years. The same kind of massive ejections have been detected again and again, all coming from the center of galaxies. This extraordinary image shows that millions of years ago, the center of our own galaxy gave off gigantic bubbles of energy, spanning about 50,000 light years. So what can possibly lie at the center of galaxies which give off these colossal outbursts? This is a panorama photo of our own Milky Way, but seeing what lies at the center is a scientific challenge.
In order to see what's at the center, why isn't it simply a case of pointing our telescopes at the core of the galaxy and just looking?
It's because of this black stuff. It's dust particles that lie between the stars. They're produced by the stars, but they're all over this interstellar space. Wherever you look, there is going to be dust. It's material that's not dissimilar from smoke, and you know how smoke blocks light. Essentially, it becomes impenetrable when you're looking along the plane of the galaxy.
Fortunately, dust is only a problem in the visible part of the electromagnetic spectrum. Andrew shows me the same view of our galaxy using a telescope that detects infrared radiation, not visible light.
And in the infrared, we can see through the dust. Looking through, we can see many more stars. There's 100 billion stars in the galaxy.
Most of the stars in our galaxy rotate around the center at roughly the same speed, about 220 kilometers a second. But that's not true for the innermost stars.
All of these stars will still be going round at 220 kilometers per second. But then as we get right towards the center, we find there's a group of stars which are actually moving in a strange way. They're moving much faster, and you can see that this one is swinging round in an orbit around something around there. It goes up to 5,000 kilometers per second, much faster, and something must be doing that.
It's by studying strange mysteries like the orbits of these stars that astronomers have come to an extraordinary conclusion.
The only possible solution for this, the only thing known to physics that we can fit inside that orbit and have that gravitational pull, is a black hole. a black hole with a mass of 4 million suns, and therefore there's a supermassive black hole at the center of our galaxy.
A black hole is formed when matter, such as a massive star, implodes, becoming so dense that not even light can escape its gravitational pull. It's now thought that there may be a supermassive black hole at the center of every large galaxy in the universe. In 2019, a team of astronomers managed to take the first ever photograph of a black hole in a galaxy called M87.
A key issue here is that the black hole itself cannot emit anything. Light only falls into it, it doesn't come out of the black hole. And what we can see is emission from material swirling round the black hole. And it's in what we call an accretion disk.
An analogy for the accretion disk of a black hole can be found in a kitchen sink. As water goes down the plug hole, much of it swirls around the rim. In supermassive black holes, some matter is swallowed, some swirls around, forming the accretion disk. The result is an astonishing buildup of heat caused by friction.
It gets to hundreds of thousands of degrees. All of the emissions from the accretion disk, which include jets, it releases an enormous amount of energy.
We're now pretty sure this is the answer to the puzzle of the giant outbursts. They're coming from the supermassive black holes at the centers of galaxies. Andrew believes these black holes have had a fundamental role in shaping the galaxies around them. The jets of high-energy particles and radiation are believed to have triggered the formation of generations of stars. Andrew has also found that these explosions of energy can blow the interstellar medium out of a galaxy, halting star formation. Galaxies come in all shapes and sizes. They range from dwarf galaxies, perhaps just a tenth the size of the Milky Way, to giant ones, many times its size.
It's now thought that there may be up to 2 trillion galaxies in the observable universe. But here's the question. Do all these galaxies just float around by themselves, moving through space serenely as independent objects, as lone travelers? Or do they come together as part of even larger structures? And how can we even answer that question?
Fortunately, to help tackle this puzzle, cosmologists can take advantage of a very peculiar phenomenon we're all familiar with here on Earth.
What you heard there was the famous Doppler effect. As the car approaches, the pitch of the trumpet is high, but as it passes me, that pitch drops.
The effect happens because as the car approaches me, the sound waves bunch together, shortening the wavelength and raising the pitch. As the car drives away from me, the waves are spaced out, lowering the pitch. Light waves do the same thing. When a source of light is moving towards us, its waves shorten, which moves them towards the blue end of the spectrum. When it's moving away, the waves are shifted towards the red. So by measuring the spectrum of light given off by a cosmic object, astronomers can tell if it's moving towards us or away from us. It's one of the uses of a technique called spectroscopy.
I'd like to give you an example of how spectroscopy works in practice. A few days ago, I asked my local astronomy club, the Hampshire Astronomical Group, to point one of their telescopes at the Andromeda Galaxy. Now, this is the nearest large galaxy to us and the one that Hubble used to make his big discovery. Using an instrument called a spectroscope, they were able to record its spectrum. And here it is. Now, there's a lot of science here, so I'll take you through gently. Here's the spectrum, this black and white image that was actually taken, and here it is again in all the colors of the spectrum. Now, this wiggly line here is the intensity of the light at different wavelengths, different colors that's coming from Andromeda. These dips here are signatures of particular elements in Andromeda, and this big one here is the important one. This is the signature of sodium. So you see this dark line here, that corresponds to the wavelength of sodium. Now, if Andromeda wasn't moving towards us or away from us, there'd be no Doppler shift, and we would expect to see this dip at a particular wavelength. We should see that dip between these two vertical lines. But in fact, you can see it shifted slightly to the left to shorter wavelengths or slightly towards the blue end. That means Andromeda's light is blue shifted, which means it's moving towards us. And from the amount of shift, we can work out how fast it's approaching us. You might well ask, so what? Who cares? But the remarkable thing is that by measuring a tiny shift in a wiggly line, we're able to calculate that the Andromeda Galaxy is heading straight towards us at 300 kilometers per second.
So, through spectroscopy, we've discovered our galactic destiny. It will take about 4 billion years, but Andromeda is predicted to hit our galaxy in a cataclysmic merging, which may even eject the solar system from the Milky Way entirely. Using spectroscopy and other observations, we now know that galaxies move through space in complex ways. Under the influence of the vast power of gravity, many of them are drawn together into what are known as galactic groups of up to about 50 galaxies. These groups can be drawn into larger structures called galaxy clusters of perhaps 1,000 or more galaxies. And these clusters can group together, forming the largest known structures in the universe, galactic superclusters. These consist of millions of galaxies and can stretch across distances greater than 100 million light-years. In recent years, cosmologists have discovered the galactic supercluster which we are part of. Over the past decade, Professor Hélène Courtois of the University of Lyon has been working with an international team of astronomers on the epic task of mapping it.
Hello, Hélène.
Hi, Jim. It's nice to see you.
Hélène worked day and night using video conference calls to colleagues at radio telescopes across the globe.
These telescopes are in different time zones, so when do you sleep?
Yes, we sleep when we can. But I love observing, so I always try to be on all the shifts.
I've seen you describe yourself as a cosmographer.
Yes.
What does that mean?
So it's someone who is making maps. I try to find out where are the other galaxies compared to our galaxy, and then I measure distances and coordinates on the sky of those galaxies. And my specialty is not only to make maps, but to map the motions of the galaxies in the universe. So I am a dynamic cosmographer. I'm going to do galaxies all my life because what I want to see when I open my computer, I want to see beauty. So every morning I look at what the telescope have been running in the night and I see galaxies all the time. I don't want to do any other job.
First, Hélène and colleagues plotted the positions of many thousands of galaxies, creating intricate 3D maps like this. Each galaxy is just a little dot. Then they measured the spectrum of every single galaxy to see if it's blue shifted or red shifted. And that meant they could work out the direction in which each galaxy is moving and at what speed. They found tens of thousands of galaxies all flowing in the same direction, forming a giant supercluster.
And they fly like this, like a dance, so the motions of galaxies are correlated, they travel together. They are not like with random motions. In some part of space, they travel together, and this is how we make this discovery.
In 2014, they made an astonishing announcement. They'd mapped the giant supercluster in which our own galaxy resides. They gave it a Hawaiian name, Laniakea. Its true size is incomprehensible to our minds, confined as we are to our earthbound scales, shapes and sizes. But there are landscapes here on our planet which can give us an inkling of what Laniakea must be like.
To help us understand what these galactic superclusters look like, cosmographers like Helene often use the analogy of a river system, with smaller streams flowing into larger streams, which then flow into rivers, all heading towards the sea.
At the largest scales of the universe, galaxies move together through space along pathways which resemble rivers. The power of gravity makes raindrops fall into streams and streams to flow downhill into rivers. In the same way, galaxies are pulled by the immense power of gravitational attraction, heading to an enormous concentration of mass. So let me give you a tour of Laniakea.
This is our home galaxy, the Milky Way. And we live within what's called the local group, which contains some of the galaxies we've met before. For example, here's the small and large Magellanic Clouds. These are dwarf galaxies that were studied by Henrietta Swan-Leavitt. They're about 200,000 light years away. Over here is the giant Andromeda galaxy, which of course is on a collision course with us. It's over 2 million light years away.
Our local group stretches up to 10 million light years across, but it only forms a small part of the structure which Helene and her colleagues have discovered.
So let's see what the whole of Laniakea looks like. Each one of these dots is a galaxy, and each one of these lines is a pathway that they follow. Our Milky Way and all the other galaxies in our local group sit in one of the streams over there.
All of the galaxies are being pulled by incredible gravitational forces along these pathways. They're all moving towards a central mass called the Great Attractor. The Great Attractor is still a mystery, but it's thought to have the mass of trillions of suns, attracting galaxies across hundreds of thousands of light years.
And there we have it, our home in the universe. Laniakea contains about 100,000 galaxies like ours and 100 trillion stars. It stretches across 500 million light years. Looking at all of this, you can see why they called it Laniakea. It's a Hawaiian term meaning immense heaven.
These giant superclusters are only just being discovered, so we're only now starting to get to grips with the way they work. From earthly scales to the rotation of galaxies, the force of gravity is well understood by physicists. But it doesn't necessarily mean we understand how gravity holds these giant superclusters together. So cosmologists like Helene use superclusters to investigate the workings of gravity at the very largest scales.
Our question, our physics question, is gravitation. How does it work on large scale? Does it work just like on Earth? And was it always the same in time? So we use the universe as a lab with huge masses, the galaxies. From the infinite small to the infinite large, it's the main question of physics of the 21st century. We still miss the full understanding of it.
By studying superclusters, a few cosmologists are beginning to question some of our most cherished scientific principles. According to our current model of cosmology, the laws of physics suggest that structures much bigger than Laniakea cannot exist.
If I look at this sheet of sandpaper, at this scale, it looks completely uniform. There's no pattern to it. But if I zoom in using this portable microscope connected to my laptop, suddenly I see structure, mottled colors of black and brown and yellow, shades and speckles, which are completely invisible when I'm zooming out looking at the whole sheet.
According to our current theory, a similar principle applies to the universe. After the Big Bang, matter was scattered pretty evenly throughout the cosmos because the same forces acted equally on everything. The power of gravity brought together galaxies and then galactic clusters, but over a certain size, gravity is too weak to bring structures together. Like my sandpaper, the universe should appear featureless.
This is what's called the cosmological principle, and it's one of the foundational pillars of modern cosmology.
But recent findings have cast some doubt on this extremely important idea. Remarkably, one of those discoveries was made by a student. Alexia teaches violin to students to help fund her way through her PhD. And while doing her research, she came across something remarkable.
It was really exciting, but completely accidental. My supervisor had this idea of using this new technique to map what's out there in the universe. And I happened to stumble across this giant, great structure. It was completely serendipitous.
The ingenious method which Alexia used involved very distant objects called quasars. These are immensely bright centers of galaxies, billions of light years away, thought to be powered by supermassive black holes. For Alexia, they were extremely useful because she could use them as if they were spotlights, shining a light on the dark corners of the universe.
We're going to use these two torches to represent quasars, these very distant, powerful sources of light. Now, you have a simple demo here, this plate of glass. Tell me what these blobs are.
These little blobs here are representing faint galaxy and galaxy clusters. Now, without the quasars, we wouldn't be able to see them. They're too faint and too distant. But with the quasars, they essentially act like a torchlight that illuminates this faint matter.
As the light passes through a galaxy, some of it is in effect blocked.
We can see that some of the light was absorbed, and therefore something must have absorbed that, and therefore there is matter lying there.
Using this method, Alexia has been able to create a 3D map of a huge chunk of the universe. And she seems to have found a pattern. These red blobs are all galaxies or galactic clusters, and together they appear to form a giant structure in the shape of an arc.
We've used 3 different statistical tests, and all 3 of the tests show that the giant arc is actually more than just a random fluke.
That it's really there. Why is it so unexpected and exciting?
So we have this thing in cosmology known as the cosmological principle, and it says to us that on the largest scales there should be no structure or pattern in the universe. The cosmological principle has a specific cutoff limit, and that's estimated to be about 1.2 billion light years. But the giant arc here is over 3 billion light years wide, so it begs the question how something like that can form in our current understanding of cosmology.
The giant arc is so big that if we could see it from Earth, it would look 35 times bigger than our moon, even though it's 9 billion light years away. The reason it's so mysterious is because it's too big to be held together by gravity. And it's not the only one. Even bigger superstructures have been found, such as the Hercules Corona Borealis Great Wall, thought to be 3 times bigger than the giant arc. It's early days in the story, but this debate could be a game changer, because all our theories of how the universe was formed after the Big Bang are based on the cosmological principle.
Time will tell, I guess. It's still too early to be sure.
It's still too early, but everything is built on top of this assumption of the cosmological principle. So it's kind of like taking the bottom piece of a Jenga puzzle out and the whole thing collapses.
Carrying out investigations at these mind-boggling scales continues to challenge our most cherished beliefs, transforming everything we thought we knew about how the universe behaves and how we came to be here. And I can't wait to see what we discover next.